Okay, these are some more notes from section 7.1, and this is example. Now, if you look over in your text on page 380, they kind of did the example 2, and we're just going to be looking at example 2, and they did the 2A in 1 second. So they kind of show all the work in detail over there, and they came up with the new position, which was the initial position plus the displacement of the actual position was 16/3. So now what we're going to do is we're going to just do the second part, and they wanted to find the displacement 0 to 5, and they didn't show as much detail on that, so I thought I would go over that. And if you do have any questions on that first part, just let me know, but it should be pretty straightforward because they did do a lot of detail. They did model. They showed you how, again, we talked about building the integral, where we use all these little displacements over AB, and then we came up with this. They came up with this interval. In this case, it was from 0 to 1 of t dt. And we're going to be doing from 0 to 5, so we're going to find the displacement. Now, I set this up a little bit differently than the way they modeled that with the small displacements. It ends up being the same. It's just kind of the way I did it in college. So you could kind of model it and take a look at the way they set up the integral in example 1 over on page 380. And then you can see this. This is a very, very similar. I'm just not approaching it from the little increments approach, which is it's a good technique to be aware of, and this is just a different technique, so whatever's your pleasure. But like I said, this is the way I did it in college and kind of sticks with you. So what we did was we know that in this particular case, this is the velocity function. This was given to us. We want to find displacement, so we know velocity is equal to the ds dt, the derivative of s with respect to t. So I just put the t on both sides, the dt on both sides, or multiply both sides by dt, or move the dt from here to here. And then I took the antiderivative of both sides, and I'm going to get the displacement. Now this is going to be over 0 to 5, so that's why I'm going to go the integral from 0 to 5. I'll show you later what happens if we just take a general antiderivative, not a indefinite, I should say. Okay, so let's take a look at this. So this is going to represent, now since I'm going from 0 to 5, this is going to represent the displacement on 0 to 5, delta s. So if we take the antiderivative of t squared, we get t cubed over 3. And then what I did was I put this up on top to make it a -2 so I could take the antiderivative easier. And then I can think of this as u to the n du. The derivative of 1 is just 1, so we've already got the du. So we can apply the power rule. So I add 1 and then divide by that. And then it takes the antiderivative, and I'm going to evaluate it from 0 to 5. And I believe this is the way I did most of the homework problems. Okay, so delta s, the change in s, equals this t cubed over 3 plus 8 over t plus 1 from 0 to 5. And then we evaluate that, so that's going to be 125, 5 cubed is 125 over 3, 8 over 6, 5 plus 1 is 6, minus 0 over 3 plus 8 over 1, 0 plus 1 is 1. And that ends up being 41 2/3 plus 1 2/3, so that actually ends up being 43. And then minus 8 was 35. So that was my displacement. But they actually wanted to find they actually wanted you to find the final position. So the final position would be the initial position plus the displacement, delta s plus s sub 0. We found delta s through this antiderivative process of being 35, and if we add that to the initial position, you end up at 44. And like I said, they come up with the integral by using the small increment method. That's very valid and a very valuable method, way of doing it. And I do it kind of like solving a differential equation over a definite interval. It just works out to be the same. This notation-wise might be a little bit easier to follow. But again, using the little increments and the summation and switching that to an integral over an interval, that does help in some more general type problems. This works really good for your physics problems of motion, where you know ds dt is v of t, and dv dt is a of t, so that maybe will help. Okay, now the next section down the bottom where it says support graphically, don't take a look at that or up on top of page 381, because that's using parametric equations, your parametric mode, and we haven't really gone over that, so just kind of skip over that. But what I do want to also talk about now is this exploration 1 over here, and it says revisiting. So let's take a look at this. It says revisiting example 2. And this is kind of what they're talking about. What they're doing is they're coming up with a position function, and in a way, I'm kind of doing what they're doing, but a little bit more general even. So just kind of follow what I'm talking about here, and hopefully this will help. And what we're going to do is we're going to come up with the actual position function. So we won't have to worry about the initial and the delta. We'll all that all combined together. So we're going to solve this differential equation. So we know that v of t, the velocity, equals ds dt, and this is my v of t, and this is my particular value. So I know when t is 0, then my position s is 9. So what I can do is I can, again, like I did before, just separate the t, so put the dt over here, then take the antiderivative of both sides, and I get this. But now this is not going to be over a particular interval from 0 to 5. This is just going to be in general. So this is going to be a general, this is going to be the solution for a general differential equation with this initial value. So it's not going to be over a particular interval as far as this is concerned. So it's going to give me my position, actually my position, not my delta s, but it's going to actually give me the s of t. And you'll see where this is real handy. Overall, so we just take the antiderivative of this will be t cubed over 3 plus 8 over, and the same thing. So this is the antiderivative is the same as we did in the previous page, but only now I'm going to be adding a c. I'm going to adding a constant of integration. But I do have a particular value, so I can find that constant. So when t is 0, s is 9, so s of t is 9. When t is 0, so if I put 0 here and 0 there, what do I end up with? 0 plus 8 equals c. So if I subtract 8 from both sides, c equals 1. So I can put the 1 in here. And now I have a position function for s at any given time. Now that takes into consideration the displacement and the initial position, because that gives you just the position. So this is really nice, and you'll see if we do this for 5, we'll put 5 in. We get 125 over, again, 8 over t plus 1 or 0, 5 plus 1, because we're finding the position at 5, 8 over 6, and then plus my constant. Well, this ends up being the 41 and 2/3 looks familiar, and the 1 and 2/3 looks familiar, but this 1 is different because this takes into consideration the initial position. So we end up with 43 plus 1 is 44, and that's what we got in the previous problem. So go back and take a look at that. And you see, get the same thing. There's your delta S and your S sub 0, 44. Okay. Now we could always figure out the delta S because we know the initial position is 9. So if I subtracted 9 from 44, I could get 35, so I could figure out the delta S. So going this way, is kind of nice in a lot of ways. Now, let's go back and say, well, will this work for the first part of the example, part A of example 2, where we wanted to find the position, find the position over 0 to 1. Well, then we just want to find the position when t is 1. And I just did this over here on the side, and I put 1 in here. So that'd be 1 cubed, which is 1/3. 8 over 1 plus 1 is 8 over 2 plus 1. And that's going to be 1/3. And then 8 over 2 is 4 plus 1 is 5. So that's 16/3. And that's what they got on the middle when they had the new position. On the middle of page 380, you see the new position is 16/3. So we found it quite easily just by substituting into that quasi-general differential equation. It's specific because I do have the initial value, so it's a definite differential equation, but it is actually the position function. So I found a working position function, and that's a good technique to know. Okay, that's a very good technique to know. So you got a couple ways of looking at the same problem. So whichever you like. I know sometimes it's confusing for me to show you two different ways, but then it does give you some options, and try to do it both ways. And some of the problems are kind of long, so probably won't try that, but be aware of both approaches to the same problem. Okay, over a specific interval, that's the first thing we did, or just find a differential equation that gives us the position function given any t, and then you can solve for the t. Okay, I hope that helps. And we'll do some more notes and a couple more examples in just a moment.